Now we'll see Bellman-Ford algorithm's working principle. It is very simple. In Bellman-Ford algorithm, what we do is exactly v minus 1 times we relax all the edges of the graph. So if you do that, automatically every vertex will get its shortest distance. Why, we will see. So we relax all edges, okay, all the edges. So let's do it first. After that we'll try to understand why. Because of that, automatically shortest paths will be calculated. Let's give particular values to them. That's it. This is Bellman-Ford algorithm. Example, a to d is 1. Let's take a to c 2, a to d to c 1, and b to c something 2, and a to b 3. Let's take source as a, right? So this is source in this problem. So v minus 1 times, number of vertices here 4, right? That means 3 times we are going to relax the edges. What is the order of relaxation? Nothing. So any order you can relax, but in the same order you have to relax 3 times. Example, let me relax the edges in this order. First AD, after that maybe AC. I am taking random order. AB, after that we have 5 edges, right? Then AC, AD, AB, followed by DC, followed by, let's take directions, DC, AC, C to B, B to A, doesn't matter. Okay, so first we relax A to D, then A to C, then A to B. Do we have A to B? No. Then we relax B to A, then one more edge is C to B, we relax. After that, one more edge, D to C. Let's do it. If I do, what happens, we'll see. I am relaxing now A to D. If I relax A to D, if source is A, what happens initially? First of all, Bellman-Ford algorithm should be initialized with D values. So D of D is, directly write it. Initially its D of D is infinite. Infinite, infinite, everyone's value is infinite except source. Source has 0. Because source knows that shortest path from source to source is 0. Now let's relax AD. When you relax AD, so 0 plus 1, 1. D is going to get 1. Right? Now A to C. So C is now having infinite, then this distance is better. 0 plus 2. We know the formula, right? Whenever you relax an edge A to C, we formula is, using the A, we are relaxing, correct? Distance of A plus weight of AC versus distance of C. So if this is better than distance of C, we update distance of C, right? Let's do it. So what is distance of A? 0. 0 plus 2, 2. 2 is better than infinite, correct? Then update it. Now distance of C is 2. So relaxation step is done for A to C. Then B to A relaxation. When you do B to A relaxation, using B, we are going to relax A. That is easy to understand. So distance of B plus weight of BA should be compared against distance of A. So what is distance of B now? Infinite. Infinite plus anything is infinite. You have already very long answer. So you can't teach distance of A. You can teach distance of A only if you have better answer. That's why. That is the such a way formula is written, right? So A will not be updated. So but relaxation is done. Then C to B. So if you do C to B, so distance of C. What is distance of C? Now 2. 2 plus distance weight of CB. 2. 2 plus 2, 4. 4 is better than distance of B. Now see, B learned something better than infinite, right? This is done. Then distance of DC. So distance of D, 1 plus DC value 1. 1 plus 1, 2. 2 and distance of C, 2. See, D is teaching C, but that value is not better than current value, right? Already distance of C is 2, correct? So if it is 3, we would have improved it by writing 2. So don't update it. If it is already same, don't update unnecessary. Now, only one phase of relaxation is done. How many times you have to do that? V minus 1 times. V is what? 4 vertices, right? 3 times. Let's do quickly A to D, again A to C, B to A. This is second time. C to B, D to C. Start A to D. Distance of A, 0 plus weight of AD, 2. 0 plus 2, 2. 2 versus distance of D, 1. So already D has better answer. So relaxation is done. Next. Sorry, distance of A, 0. 0 plus distance of AD, 1 is better than 1. So I forgotten, actually I relaxed AC, but we have to relax AD, right? Because of that D won't get a correct different answer. AC, distance of A 0 plus weight of AC 2, 0 plus 2 2, but it is already having that answer, don't relax. B to A, distance of B 4, 4 plus 3 BA 7, 7 is better than 0, no, don't relax. So distance of C to B relaxation, distance of C 2, 2 plus weight of CB, C to B 2, 2 plus 2 4, already B got it correct. Then D to C, distance of D 1, 1 plus weight of DC 1, 1 plus 1 2. So same thing is repeating, right? The reason is what, already that ABCD got the correct answers, but you have to do it in the algorithm. A to D, A to C, B to A, C to B, D to C. This is the idea about Bellman-Ford. If you do 3 times, what happens I will tell you. Everyone will get shortest path. What is the reason, sir? We realize that everyone is getting shortest paths. But why? I will tell you. Example, let's say source is S. X is one vertex. Why X is going to get shortest path? I will tell you. So rather than S, X, let me take ABCD. A is source, right? Why D will learn the correct answer? I will tell you. What is the actual shortest path of A to D? What is the actual shortest path? Is directly A to D. Now my question, already I told you in path relaxation property. Really this is the shortest path from A to D. If you relax AD at any time, automatically D will learn the answer. That is a theorem, right? So that's why D will learn it. But sir, why B will learn? What is the shortest path from A to B? See, what is the path? Did you remember? The shortest path is 4, right? Like this, A to C, C to B. But are we doing A to C, C to B? See, we are doing A to C, C to B. That's why. But sir, why multiple phases? Sometimes what can happen, I will tell you. Consider this scenario. Your vertices are like this, 1 to 2, 2 to 3, 3 to 4, let's say. And let's say source is something 1. Okay. Distance of 1 is, source is this one, distance of 1 0, all are having infinite. What can happen is only one time if you relax all the edges, so everyone might not get shortest answer. Example, this value is 1, this value is 1, this value 1. Try to relax everyone. If you relax in this order, because we don't know our underlying data structure, right? Bellman-Ford algorithm says that relax all the edges. What if the order of edges you have taken is like this, 3 to 4, then 2 to 3, then 1 to 2. So if you relax in this order, because we don't know, right, what might be the correct shortest path order. If you relax in this order, what can happen we will see. First, let me relax 3 to 4. So distance of 3, infinite initially, right? Let me write it. So distance of 4 infinite, distance of 2 infinite, distance of 1 0, correct? Yeah. I am relaxing 3 4 edge. Blind formula is distance of 3 plus weight of 3 4. Distance of 3 infinite plus weight of 3 4 1. Infinite plus 1 infinite. Already 4 is having that infinite answer. That's why no learning. Then 2 to 3. If you relax 2 to 3 edge, distance of 2 infinite plus weight of 2 3 plus 1. Nothing. So no learning because of this one. Next, distance of this one 1 to 2 relaxation. This is the only relaxation which will work. So this time what happens, definitely this step is going to be fruitful. Why? Because one is having some proper information. So I am relaxing 1 to 2 edge because of this. He is the now most knowledgeable person, right? He knows shortest path. He is going to teach now 2. How you see? Distance of 1 0 plus weight of 1 to 1. 0 plus 1 1. Is it not better than 2? Current value? Yes. Now 2 got better answer, 2 become knowledgeable. But when you do only one time, 1 got the correct answer, 2 got the correct answer. But what about 3 4, right? So that's why. But sir, how can we say that definitely after some time 4 will learn the correct answer? How you guarantee? How many times we have to do that? That's why. So how many times we have to do this step, I will tell you. Finally, so this order, I don't know what order you are using. Really 4 will get the shortest answer only if the relaxation happens in this order. What is that? 1 to 2, 2 to 3, 3 to 4, because that is the shortest path from 1 to 4. The edges in shortest path of 1 to 4 are 1 to 2, 2, 3, 3, 4. In this order if you relax, then only 4 will learn correct answer. But if I do only one time this kind of relaxation, this order might not be guaranteed. But if you do one more time, let's do one more time, 3, 4, 2, 3, 1, 2. Then at least, still we cannot guarantee. Why? See, in this one, 1, 2 is done. One more time if you do, then here 2, 3 will be done, you see. Sir, 2, 3 here also will be would be done, right? But the order you see, so 2, 3 is preceding 1, 2. 1, 2 is successor. So here 2, 3 is predecessor of 1, 2. That's the problem. But if you do 2 times, then here this 1, 2 is going to be predecessor of 2, 3. That means 2, 3 is going to be successor. That is what I want. But still only 1, 2, 2, 3 order is maintained. But I want 1, 2, after that 2, 3, after that 3, 4 should be done. But before 3, 4 is happening here before 2, 3. Correct? Sir, can I take like this order? Can I relax 2, 3 in 3, 4 order? No. If here you are relaxing 3, 4 followed by 2, 3, then that order cannot guarantee the shortest path. What is the order we need? 1 to 2, 2 to 3, 3 to 4. That means first 1, 2, after 2, 3, after that 3, 4. But if you do 2 times, still I can guarantee 1 to 2, 3 order here. Correct? Otherwise 2, 3, 3, 4 order, but 1, 2 is not here. Sir, can I pick 2, 3 here, 3, 4 here? Yes, you can. But see the order. The order of relaxation is 2, 3 first, after the 3, 4. But in between some other relaxations happened, right? Yes, already I told you in path relaxation property. Recall. Some other relaxations, whatever happened, doesn't matter. But our relaxations, our target is what? 1, 2, 2, 3, 3, 4. They should be done in this order for that. But what if you do one more time? 1 to 2, 2, 3, 2 to 3, 3 to 4. So from here I can pick 1 to 2. From here I can pick 2 to 3. From here I can pick 3 to 4. So finally 1, 2 I can prove, I can say that 1, 2 is relaxed. After that 2, 3 is relaxed. After that 3, 4 is relaxed. That kind of thing I can guarantee. That's why V minus 1 times we have to relax the edges, all possible edges. Understand? Now, sir, what if this is the case? What is that? I have a shortest path. It is having lot of edges. After you are doing 3 times, right? My shortest path contains 4 edges like this. Edge 1, edge 2, edge 3, edge 4. Now, how can you guarantee this order? With the 3 iterations, at most you can guarantee 3 edges order, right? But what if my shortest path has 4 edges like this, E1 to E2, E2 to E3, E1, then E2, then E3, then E4. How can you pick it up now? Here you can pick E1, then E2, then E3. What about E4? So this order might not be preserved here, right? With these 3 combinations? Yes. But your graph with 4 vertices cannot contain shortest path with 4 edges. Why? There are after all 4 vertices. Example, let's say 1 and 4. If between 1 and 4, if there are 4 edges, then there are after all 2 other vertices, right? That means you are repeating the vertices. When you repeat the vertices, it forms cycle. Correct? I can say that blindly, when there are n vertices, if your shortest path contains n edges, it forms cycle first. Right? When there is a cycle, then that cannot be shortest path, because shortest path cannot contain cycle. That is obvious. If there is a cycle in shortest path like this, then I can, so why should I, I can directly go like this, right? Example, this is A, this is B. So A to B in the shortest path there is a cycle. My suggestion, why to make a round here? Unnecessarily you are consuming lot of edges. Better you go like this, correct? You can skip that cycle and we can save some distance. So hence contradiction. What is the contradiction? Saying that shortest path contains cycle. By removing it, I can get better answer. So there is no better answer than shortest path means there is no cycle, right? So that's why at most your shortest path contains n minus 1 edges, where n is number of vertices. When there are n minus 1 edges, then that edges, whatever they are, example, that edges are E1, E2, E3, so on, En minus 1, where n is number of vertices. Then if you relax the edges n minus 1 times, then this order relaxation is guaranteed. How? Simple. Here E1 is definitely relaxed. Here definitely E2 is relaxed. here E3 will be relaxed and order also guaranteed. That's why Bellman-Ford algorithm definitely works and everyone gets shortest path. But the only thing is we have to do lot of relaxations. How many times? V minus 1 times we have to relax the edges. Actually, what is the time complexity of relaxation? Everything we will see now. Okay. So before going to the time complexity of this Bellman-Ford algorithm, so I will introduce one more concept in this graphs, that is negative edge weight. What if our graphs contains negative edge weight? Consider this graph. Let's say A to B, B to C, and C to D, and let's say D to B. So B to C and C to D and D to B. Let's say edge weights are, let's take this one 3, this one let's say 4, this one let's say -1, -2. So what is the shortest path from A to B? Let's say source is A. If source is A, shortest path from A to B is definitely 3, correct? Do we have any better answer? If you make a round, we have a path, you see another path. Go to A to B, B to C, C to D, D to B back. Then effectively what happens? To come here 3, after that if you make a round, it takes effectively +1, because sum of edge weights of this loop is 4 plus -1 3, 3 plus -2 1, right? So 1 plus this 3 will become 4. That's why don't make a round. By making round we are not reducing the distance, right? So that's why I can say that shortest path from A to B definitely 3. Let's write it. Shortest path from A to A is 0. I'm just computing shortest paths in the presence of negative edges, right? Now what is the shortest path from A to C? So directly 3 plus 4, 7, correct? If I make a round, already I know that it will add +1 extra. That's why better don't make it round. So 7. So what about going to D? So it will be 3 plus 4, 7, 7 plus -1, 6, correct? Now already computed for B. So these are the values 0, 3, 7 and 6. Now the question is, can we always compute shortest paths in the presence of negative edge weights? No. If your graph contains edge weights, negative edge weights, such a way that if there is a cycle, so that cycle contains value such a way that the total value of that weights in the cycle is negative, then what happens we'll see. What I'm saying is, example, this is 2. Then overall the sum of the edge weights, if you see, negative. So that is called negative cycle. Let me call it as negative cycle. When graph contains negative cycle, then shortest distances cannot be defined properly. Let's try to understand that why we can't define. So what is shortest path from A to A? Obviously best is 0 at this moment. Remember, we don't have any other path also, right? That's why it is 0. But for A to B we have 2 paths, directly going A to B without loop, otherwise take the loop. If I take loop, there are infinite paths possible. One is A to B, B to C, C to D, D to B, second path. Third path is A to B, B to C, C to D, D to B. Don't stop, continue the loop. If you take loop once, it is one path. Take 2 times, 2 paths. Take 3 times, third path. In that way, infinite paths are possible. Let's focus on all such paths. First path is, don't take this loop. That means loop is taken 0 times, then the weight is 3, correct? So far it is best. Now another path possible from A to B, that is taking a loop 1 time. It will be 3 plus 2, 5, 5 plus -1, 4, 4 plus -2, plus 2. It is better than 3. What is the reason? Because when you made a round, that cycle was giving you -1 effective weight, correct? So that's why 3 plus -1, 2. If you take one more round, already the weight is 2. 2 plus this -1 will become +1. If you take one more round, it will be 0, then -1, -2. My question is, what is minimum here? We can't define, right? No integer is minimum here, right? So if you say -100 is the best answer, then still if you make one more round, you get -101. So what I would like to say here is, so for B, shortest distance is not defined when in the presence of negative edge cycles, correct? So I can say that finally whenever your graph contains a negative edge cycle, what is negative edge cycle? A cycle with sum of its edge weights is negative, then definitely we cannot define shortest paths for some vertices, right? Like B. Similarly for C we cannot define, because the path from source to C is that can be done with a loop. Whenever you can do that with loop, then definitely we cannot define, right? So every time by making a round, you can reduce the value. That's why problem for C, problem for B and problem for D also. That's why what I want to say is, so somehow your algorithms, like whatever the algorithm which is computing shortest path, so that should avoid this kind of graphs, right? So this is not defined. Like for b comma c comma d, shortest paths cannot be defined. Then what these algorithms are going to do is Bellman-Ford algorithm, which I am going to teach you, that can detect, if you carefully plan Bellman-Ford algorithm, then that can detect these negative edge cycles and if they are reachable, okay, and it can avoid them and it can return false answer. We are going to design a Bellman-Ford algorithm. I teach you that algorithm. So on that, what we do is we are going to detect the negative edge cycles. And how you do that, I will tell you. So what is the working principle of Bellman-Ford algorithm? In that Bellman-Ford algorithm, so we have relaxed all the edges, right? How many times? V minus 1 times. So after doing V minus 1 times, what happens? So everyone will get some shortest distances, right? Shortest distance. So after that, we do what? One more time we do relaxation. When you do relaxation one more time, then what happens? I will tell you with small example. Example, A to B, B to C. A to B minus 1, B to A minus 1 again. So somehow let's say Bellman-Ford algorithm, how many times we do Bellman-Ford algorithm for this small graph with two vertices? V minus 1 times. V minus 1 is 1 time here. When you relax all the edges one time, what happens? We'll see. So I am running Bellman-Ford algorithm here. So relaxing all the edges in one particular order, any order. Let's relax this edge. When you relax this edge, A is going to teach B. Initially this is 0, this is infinite. Mr. B, please learn a new value is 0 plus minus 1 minus 1. Yes, relaxation is done. Now relax B to A edge. So there is a mistake here. It is B to A edge. If I relax B to A edge, then B is going to teach A. Then this 0 is updated by minus 1 because, sorry, it's not minus 1, minus 2. B's value minus 1, minus 1 plus minus 1, minus 2. So Bellman-Ford algorithm is done, but it is wrong. We know that. Why? Shortest distance of A is minus infinite, which is not a integer, right? So distance, shortest distance possible from A to B is minus infinite. When will we get it? Infinite times. If you take a loop, you get that answer. But generally this minus infinite, these values are not defined, correct? So they are not natural numbers or they are not real numbers. So our problem is about finding the shortest path, which is a integer problem, right? We have to return integer, but we can't return integer because answer is not integer. In this kind of circumstances, what Bellman-Ford algorithm does is, so it will return false. That means it says that we can't compute shortest paths for some vertices. So how it returns false, how he detects, I will tell you. At this moment, I don't have clue. Sometimes if you have negative edge weights, you might get negative answers, right? It doesn't mean that there is a loop. How your Bellman-Ford algorithm detects, I will tell you. Once the algorithm is done, so what it does is, it runs one more time. Let's run one more time this relaxation step. Then what happens? So when you relax it one more time, really it is a correct problem. That means really it is having no negative edge cycle. Then what happens? Everyone's shortest paths will be settled, correct? That means everyone should have their correct answers. Now if you relax one more time, then their value should not be changed. Then only they are correct. I assume that Bellman-Ford algorithm really works correct. Then these values should be stable, right? Let's run one more time. What happens? I am running Bellman-Ford one more time. Then relax this edge. Then what happens? This will become minus 2 plus minus 1, minus 3. And again relax this edge. Then you get minus 2 plus minus 3 plus minus 1, minus 4. Right? So now A's value and B's value got updated one more time. That is the time I can say that there is a problem. That means definitely there is a negative edge cycle. Correct? In that way, Bellman-Ford algorithm easily detects it. What it does? First, complete important code is done. What is that? Relaxing V minus 1 times all the edges. Once it is done, we write one extra condition. What is that? Relax one more time. Relax once. Here if values are again updated, then definitely it is not a correct problem. That means definitely there is a negative edge cycle, right? So this is what going to happen. Now we'll see the time complexity of this Bellman-Ford algorithm. Let's begin here. So first line, initialize single source. What is initializing single source? I will tell you. Initializing single source is nothing but, so first we know that we adjust, there are two parameters. One is D, second one pi, correct? Pi is nothing but to remember who taught the shortest value to some other vertex, correct? So every vertex will have pi value. Pi of A is nothing but it's a vertex name who taught A the shortest distance, right? So that's why we maintain pi of A, pi of B. So we know that already I taught you. So distances are updated throughout the program based on the algorithms, working principle. Let's begin. So initialization is nothing but everything here, null, 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 and these values are 0. Let's say source is first vertex. Source vertex distance value will be updated to 0 and all will become infinite. This is called initializing single source algorithm. Then one more thing what we do is we create a matrix W u comma V. Okay, otherwise our input definitely already contains it. Example, you are sorting integers. What is your input? Set of integers. Similarly, when you are applying shortest path algorithms for a graph, that graph should be weighted graph, correct? Let's say it is weighted graph, then there should be a weight matrix. That weight matrix will be like this. Example, it's a matrix, two-dimensional matrix. This W of 2 comma 1, see this one. So it's a matrix where, let's say matrix name is W. W of 2 comma 1 is nothing but it contains edge weight of 2 comma 1. So between 2 to 1, the edge weight is 10, then 2 of 1 is 10. In that way, all values will be filled initially. Okay, this entire thing is done. We don't take this as time complexity. So filling these values, everything is already done before the program begins. So this is not part of initializing single source. In initializing single source, what we do is we just update D matrix and pi matrix. Otherwise, we initialize that too. And this W is already given, right? Now we'll see the time complexity. So first, before going to this algorithm, I would like to talk about a step called relax, because we are going to do this relaxation, right? So what is the time complexity of this relaxation? If you see the relaxation, what it is doing, there is a D of V value, there is a D of U value, there is a W of U comma V value, correct? So we are comparing D of V versus D of U plus W U V. So this takes 1 unit of time to access because it's a matrix. W of U comma V entry will be somewhere here. We fetch it. It takes 1 unit. So fetching array location takes 1 unit of time, right? Within constant time, this step will be done. After that, if there is a difference, like if this D of V really bigger than this one, then we update it, correct? Updation also takes 1 unit of time, right? So after that, we update this pi of V, right? That is again an array. To update something in array, so again it takes 1 unit of time. So there are finally 3 units of time. So in this algorithm, we are going to update only D matrix and pi matrix, not more than that. You remember, there is no hidden data structure. So what is the time complexity of doing this relax step? Just constant time, remember it, okay? So let's assume this as some constant. Now we'll come to the main algorithm. So in main algorithm, first step is initializing the single source. Already I told you, initializing single source is nothing but creating an array like this and creating one more array for D and filling them, right? It takes, because there are V vertices, it takes V time, right? Now after that, this for loop. What is this for loop is going to do? This for is going to count the number of iterations. How many times we are running this for loop? V minus 1 times. That's why time complexity of this line is V minus 1, right? So asymptotically V. Now come to this line. What are you going to do here? We are going to take every edge from the edge set, correct? So assume that edge sets are, let's say, represented as adjacency list or whatever. Finally, you are picking up every edge. So maybe you can assume that they are collection of edges. Maybe they are a linked list. So in this linked list, you are picking up one by one every edge and you are processing them. What is the time complexity of taking one edge, 1 unit of time? You have to process how many edges? E edges. That's why the time taken is E, correct? Now, do relax step, but be remember here this for is under this for. How many times this for is executed? V minus 1 times. Then V minus 1 times we have to run this for loop. If you run this for loop 1 time, it takes E units of time because there are E edges to be processed, but we are doing that V times, correct? V minus 1. So I can say that this line will be executed E into V minus 1 times, right? The time complexity is E into V minus 1. Let me summarize. The time complexity of this for loop is just E, because we are picking the edges. But how many times you did it? V minus 1 time. That's why E into V minus 1. Now come to relax step. How many times this relaxation step is done? Because this relax is under this for. So for this for is executed E into V minus 1 times. This relaxation also done in E into V minus 1 times, right? Approximately E into V minus 1. Now the question, what is the time complexity of each relax step? Already I told you constant, right? So some constant. I can say overall it is, let's summarize it. This is V. This is V. This is E into V minus 1, of course, which is nothing but asymptotically EV. So this is again E into V minus 1 into constant, which is nothing but E into V. Now after that come to this line. For every edge belongs to U comma V belongs to edges of graph. So far you understand this algorithm. Already I taught you algorithm, right? Don't worry about it. So we just relax every edge V minus 1 times, right? Now this step you see, for every edge belongs to your graph, again you have to do relaxation. This is already I told you to detect the negative edge cycles, right? What I am going to do is, once this Bellman-Ford algorithm is done, this is a core part of Bellman-Ford algorithm. After that, the sixth step. In this sixth step, one more time you relax all the edges. That's why for every edge belongs to your graph, relax, that means this is relaxation step you see. If D of E greater than D of U plus W of UV means what? Still D of E is bigger than D of U plus W of UV means definitely, so there is something mistake in the graph. That means there is a negative edge cycle. That is the only reason that happens, correct? If all are positive edge weights, we know that Bellman-Ford algorithm is going to work properly, and it will because of that all the vertices will have their shortest paths, right? Once everyone gets shortest paths, once you do this step one more time, so they will not be updated, but again they are updated means there is a problem. That means there is a definitely negative edge cycle. Already I taught you, right? So that's why this is important step in Bellman-Ford algorithm. So we return false. We say that we can't find out the shortest paths because it is undefined for some vertices. Simply we throw an error. Otherwise we return true. If this condition is false, then definitely there is nothing wrong. So we return true. Finally either we return false or true, depends on this condition. What is the time complexity of checking this one? Very simple. For every edge you relaxed. Relaxation takes constant time. And how many edges you have taken? E times. That's why this line takes E. Now here this two steps takes constant time, but how many times you run it? Exactly E times. That's why E into constant, which is E, right? So overall if you see the time complexity of Bellman-Ford, we have V's plus E's plus E into V, correct? Let's write it, V plus E into V. Let's simplify it. So definitely E into V is bigger than this V and E, correct? So the product of E into V definitely bigger than V plus E. I assume that, let's say, E value, number of edges are not 0. At least we have one edge. Then definitely E into V definitely greater than V plus E. So I can take it, higher order term. So Bellman-Ford algorithm, that's why time complexity E into V. In the worst case, number of edges in a graph is, let's say it is complete graph, then definitely number of edges in complete graph, we know that V into V minus 1 by 2 if it is simple graph, correct? That means approximately they are V square by 2, which is V square. So I can say number of edges in a complete graph is V square. So V square into V cube. So for any graph which is almost like a complete, that means any graph which has lot of edges, that will have V square edges approximately. For that graph, Bellman-Ford's algorithm time complexity V cube, otherwise EV, both are same. Whenever I say EV, so I am representing the answer with edges and vertices. Whenever I am writing V cube, that means I am converting edges into vertices. But definitely in the this is worst case scenario, V cube, correct? Strictly speaking, I mean the proper usage of time complexity is EV. Definitely this will be better, rather than again analyzing E, because we don't know number of edges in a graph. It may be 1, maybe 2, maybe 3, correct? That's why don't touch this E. Directly you say E into V, correct? So if you want to say worst case scenario, then E will become V square, that will become V cube. That's a separate issue. But Bellman-Ford time complexity E into V, okay?